I'm going to be presenting my doctoral thesis on the experimental and numerical characterization of vertical sloshing. My Ph.D. thesis was born in the context of the sloshing wind dynamics project, which is a European Horizon 2020 project that has the goal of investigating the effect of fuel slosh in wind vibration damping. The project has a consortium made up by industrial, academic, and research-based partners that come mainly from Europe. And one of the secondary goals of the project is to combine different methodologies, such as experimental, numerical, and reduced order model-based methodologies to achieve this goal. If we go back in time a few years, in the Airbus laboratory, the protospace laboratory, the experiment that you're seeing here was conducted. This is what we're going to be calling the protospace experiment. Basically verified that when we put liquid inside of the tank, inside of the beam tank system, it dampens the vibrations. So what you're seeing here, it's a cantilever beam and a 7-compartment tank has been mounted on it. This setup has to be broadly representative of a wing with the baffle tanks. And they conducted 2 types of tests. First of all, they conducted what we're going to be calling dry tests, which basically it's when we empty the tanks and we make the system oscillate in a decay manner. And then we're going to replace a portion of the mass with liquid mass, filling the tanks up to a filling level, and we're going to repeat the same experiment. And what they saw is that in the wet mass experiments, we see an increase of the damping ratio when compared to the dry tests. And they also observed a slight increase of the frequency when compared to these dry tests. So then when the project was formed, it was thought that it was a good idea to simplify this problem and take into account only the vertical motion of the experiment to understand really the physics behind this problem. And that's where my PhD thesis begins. And it has the main objective of understanding the physical insights of the influence of violent and vertical sloshing flows in the damping of 1 degree of freedom systems. And these 1 degree of freedom systems are going to be excited vertically only, okay? For that purpose, we're going to build and design an experimental decay facility. We're going to perform as well a dimensional analysis of the problem that will allow us to identify the relevant parameters of the problem. Then we're going to test different cases, varying filling levels, liquid states, and densities, and we're going to build an experimental and numerical database that includes all these test cases. And finally, we're going to expand the capabilities of the Aqua GPU's VH code to deal with multi-phase free surface flows, which later we will see that may or may not have an impact in this problem. So let's start with a dimensional analysis of the vertical sloshing problem. We have a tank of dimensions height h and length l. The width of the tank is also going to be h, so that's why I'm not including it in the outline. And this tank is going to be attached to a wall via a spring damper element with stiffness k and damper coefficient c. The whole setup is going to be affected by gravity g. And inside of the tank, we're going to have a liquid of density rho and viscosity mu that's going to be filled up to a certain liquid height HL. In the free surface, we're going to encounter some surface tension forces modeled via the coefficient sigma. We will also have the meniscus angle theta, and then we're going to have a lighter phase or a gas phase with density rho A and viscosity mu A. And we're going to deflect the system a certain initial amplitude y0. We're going to choose for our dimensional units the tank of the height as length. The time is going to be 1 over the natural frequency of our system, and the mass is going to be the liquid mass. And we're going to be focusing on the total dissipated power of 1 wet test. And this dissipated power is going to be depending on all the list of parameters that I just mentioned. If we non-dimensionalize the dissipated power with the dimensional units that we chose, we see that the total dissipated power of 1 wet test has to be proportional to the damping ratio of that wet test. And the list of parameters now takes the non-dimensional form, and we see the density ratio, we see the Reynolds number, viscosity ratio, filling level, the gravity-based fruit number, we have the structural damping from the dry test, the tank aspect ratio, the initial non-dimensional amplitude, the mass ratio, Weber number, and meniscus number. And we have to underline that we're focusing on what the liquid is dissipating. So from the total dissipation, we're going to extract the liquid-induced dissipation that we're going to see as the subtraction of the sloshing of the wet damping ratio minus the structural damping ratio, which is this sine delta G. In that way, we can eliminate the structural damping ratio from our dimensional relationship. And just to recap and to summarize our dimensional analysis, we have our list of parameters that I just said, which are explained in the table, and some of them we're going to study from an experimental point of view, and some of them we will study from a numerical point of view, and some of them from both. It's worth noting that there are some numbers, for example, the Reynolds number, that we will only be able to vary from a numerical point of view, since varying the viscosity of the liquid, it's actually pretty hard to do experimentally, or for example, surface tension, that's also hard to study experimentally. Small caveat, there are two numbers, which are the density ratio and the viscosity ratio, that are required to perform multi-phase simulations if we want to analyze them numerically. And just to finish this section, I should highlight that it's common practice in sloshing problems to perform a fruit scaling, but this time we're gonna take as our most relevant number the inertial fruit scaling, which is proportional to the non-dimensional initial amplitude. And we're gonna try to answer the question of which of one of these parameter lists, these non-dimensional groups, are relevant in the sloshing-induced dissipation. So let's start with the first methodology that I present in my thesis, which revolve around the decay single degree of freedom experiments. So some years ago, I built and designed the experimental facility that you're seeing in the picture, which basically is a tank mounted on a mechanical guide that it's allowed to oscillate freely. I separated this setup into 9 items. We have on the top of the setup a load cell that's going to be measuring before setup point. The load cell is joined with the upper set of springs with a metallic plate. We have an upper set of springs. We have a lower set of springs. Then we have a laser sensor that's going to be measuring the position of the tank. We have the mechanical guide that restrains the setup to move in 1 degree of freedom only. We have the accelerometer that will measure the acceleration of the tank. We have the tank, and we have our release mechanism, which is going to be a pair of solenoids. And just to underline, what we're measuring in this setup are 3 things: the tank acceleration, tank position, and also the force at the load cell. So exploiting this setup, we will perform many tests varying different parameters. And what we want to test is if the inertial fruit number is our most relevant dimensional number, which is proportional to the non-dimensional amplitude. If we conserve this number, then we're going to have some scaling laws, some fruit scaling laws, and we can define a scaling parameter lambda, which is going to be the height of the tank divided by the height of the tank at the wing. And if we conserve this number, then the frequency should scale as the square root of lambda, as the fruit scaling laws dictate. And we selected 3 different scales: scale 1 to 6, which is the smallest one. Then we have a medium scale 1 to 5, and the biggest scale, which is 1 to 4. We can compare and see the parameters of these scales and compare them to the wing size and see that they follow the fruit scaling laws. And for these 3 given scales, we're going to perform a filling level variation study. We're going to change the liquid density. We're going to test different liquids, and we're going to change the initial amplitude of our system. And I should recall that in total we're going to perform 85 different test cases, and the mass ratio, which is an important number as we will see later, is not conserved between tests. Now, how do we derive the liquid action that exerts to the single degree of freedom system in our setup? For that purpose, we're going to divide our setup into 3 different bodies. Body 1, which is the load cell; body 2, the metallic plate; and body 3, which is going to be the tank. By applying Newton's second law of these 3 bodies, we get 3 force balances. The first force balance tells us that the compression forces acting on the load cell are equal. This is pretty straightforward, and we're going to call that measurement T. The second force balance allows us to correlate the spring damper force with the load cell measurement, and will allow us to relate the measurement from the load cell with the spring damper force. And from the third force balance, we have that the tank mass plus the mass of the springs times acceleration, it's equal to the sloshing force minus 2 times our spring damper force, which is already related to the load cell measurement. So by joining these 2 equations, we can end up and say that our sloshing force is going to be our total structural mass times acceleration of the tank plus the corrected load cell measurement. Then we're also going to be looking at the damping ratio of our tests. For that, we're going to take our acceleration signal and we're going to perform the Hilbert transform of this signal. This will allow us to calculate the envelope function of the acceleration signal. And we're going to assume, following the methodology started from Cooper and his team in 2017, that this envelope follows a simple decaying exponential function. And in the exponent of the exponential function, we have our damping ratio. So if we take the logarithm of the envelope as we're seeing here, we can actually perform a linear fitting, and the slope of that linear fitting is going to be contained the damping ratio information. Then we're also going to be calculating the phase shift between the sloshing force and the tank position. So by filtering our signals at a frequency that's close to the natural frequency of the experiment, we're able to identify the maximums, the maxima and minima of both signals, tank position and sloshing force. And we see that they are somewhat shifted. So for each one of these shifts, we can multiply by the natural frequency of our experiment, and we will get the phase shift between the force and the tank motion. Now you're seeing here a video of the reference case experiment. We're going to be calling reference case to when we're using liquid as water as liquid, 50% filling level, and 10 G of initial acceleration, which are similar to the ones that we encounter in an aircraft wing. Now, if we analyze these acceleration signal of these experiments, we get the following 2 curves. Here you're seeing a wet mass experiment, the one you just saw in the experiment, and the dry mass counterpart. And this is actually something we published in the Journal of Fluids and Structures in 2021, where we analyzed this test case. So we see from first of all, that the decay rate of the wet mass tests are higher than the decay rate of the dry mass tests. And we can actually relate some of the snapshots of the experiments to the acceleration signal. So for example, we see that when the accelerations are pretty high in the beginning of the experiment, the free surface is going to start creating a ripple that forms some really tailored instabilities that will grow and impact the upper tank wall. This is actually the inverse of the classical Rayleigh Taylor instability, since classically the acceleration goes in the downward direction and the density gradient goes in the upward direction. This time it's the opposite. The acceleration goes in the upward direction and the density gradient goes in the downward direction. Then we're going to have a very chaotic regime with many liquid impacts. There are going to be bubble formings and jets formings. And finally, when the tank motion is very, very low, a standing wave-like regime is going to start developing. And we see, and we verify the hypothesis of the project that when we include liquid in our tests, we increase the decay rates, and we see a slight frequency increase when we compare to the dry tests. So then we can replicate this experiment for the 3 scales, 1 to 5, 1 to 4, and 1 to 6. And we can scale up all of our magnitudes to the 1-to-1 scale using the fruit scaling laws that I mentioned before. So the acceleration needs no scaling, but the time does. And we see that, first of all, that the 3 scales present different decay rates. We will get to this later. Each one of these tests presents a different frequency, as shown here. If we scale up this frequency, we see that they match, and they match the wing frequency, which is 3 Hertz. We also notice that in one experiment, the frequency remains more or less constant throughout the duration of one experiment. And then by looking at the forces, we see that the forces are, when they are scaled up to the wing size, they're pretty similar at the beginning, but then they present different decay rates as expected, since the acceleration is also presenting different decay rates. If we look at the logarithm of the envelopes of each one of these cases, and we compare them to the dry test counterparts, we see that for the 3 scales, we have an increase of the damping ratio. But this damping ratio is different from one to the other one. Actually, this is happening because the mass ratio, as we foreshadowed before, it's not being conserved between scales. when we increase the mass ratio, we see that we're increasing the damping ratio as well. So for example, we go from 5 to 5%, 7.4, and 13.35. And from the reference case, we're going to be taking the sloshing-induced damping ratio, so the subtraction between wet and dry, and the maximum sloshing force to reference all of our other studies and see the influence between with respect to the reference case. So the first experimental campaign that I'm going to be talking about is the filling level variation campaign, where we have a liquid, which is going to be water. Initial acceleration is going to be 10g, or in non-dimensional units, it's going to be 1. And then we're going to vary the filling level from 10% to 90%. And what we see is when we vary the filling level and compute the damping, we see a maximum damping region between 40 and 60%. Actually, the maximum damping is obtained at 50%. Now, why is this happening? This is something that actually I asked myself a lot during the Ph.D. thesis. And the conclusion that I arrived to is that when we increase the filling level, what we're increasing is the sloshing force as expected, because we're increasing the liquid mass. But the phase shift is going to start decreasing. Why is this phase shift decreasing? Because as you increase the filling level, the gap between the liquid and the tank walls is going to start diminishing. So it's going to take shorter time for the liquid to hit the upper and lower tank walls, which is going to decrease the phase shift. And these two opposing trends will form the damping trend that you're seeing in the upper graph. The second study that we can make is to change the liquid density. And here we're going to have a constant filling level, a constant initial amplitude, and we will vary the type of liquid. We tested kerosene, diesel B, oil, water, and tetrachloroethylene in increasing order of density. I underlined in red the oil case because the oil presents a high viscosity, which is really affecting our measurements. It's something we will see later. When we increase the density, what we see is that as we increase the liquid density, the damping ratio is increasing. Now, this is something that we could see as straightforward since what we are doing really here is increase the mass ratio, the ratio between the liquid mass and the structural mass. As we increase the liquid mass when increasing the density, the sloshing force is going to start increasing. And because the force transmitted to each one of these liquids, it's the same, but the mass is increasing, the liquid accelerations and therefore the liquid velocities are going to start diminishing, which is going to take higher times for the liquid to impact the upper and lower tank walls, which translates into an increase of the phase shift. Now we can change the initial amplitude of our experiment, keeping the same filling level and same liquid. And we're going to vary the initial amplitude from more or less 1G to up to 10 Gs. And when we vary the initial amplitudes, we actually see two different trends. We see that when we increase the initial amplitude, the damping increases up until the threshold value, which is around 0.4 more or less. And after this threshold value, the damping ratio is going to start decreasing. Now, why is this happening? We can explain by looking at the second graph. We see that the vertical sloshing force is going to increase with the initial amplitude as expected in a more or less linear manner. Now, the phase shift is going to present this this trend that is composed by two different subtrends. Let's start by explaining why it's decaying after 0.4. When we increase the initial amplitude, we're increasing the inertia we transmit to the liquid. Therefore, the velocities are going to be higher, and it's going to take less time, shorter times to hit the upper and bottom wall tanks, which is going to translate in a decrease of the damping ratio, of the phase shift, sorry, which then translates in a decrease of the damping ratio. And then, to explain the first part, we're going to take a look at these pictures. What we noticed is that for a very low amplitudes, in the first few cycles of the experiment, the relative motion between the liquid and the tank was very, very little. So the phase shift was very, very low because there was very little relative motion. But as we increased this initial amplitude, the relative motion of the liquid started before up until the saturation point, which is 0.4. Finally, we're going to be looking at the dissipated power of our experiments. When we're talking about dissipated power, we're talking about dissipated power by the sloshing force that we compute multiplying the sloshing force times the tank velocity Then we're going to time average this dissipated power and non-dimensionalize it using our dimensional units. And we should check out that this non-dimensional dissipated power is proportional to the sloshing-induced damping ratio. So we take our 85 cases and we plot them here, and we see that for the 3 scales, this checks out, and the linear fitting performed suggests that the slope is very close to 1. And then we can map these 85 points and present this dissipated power in a phase shift sloshing force intensity map. What we see is that for higher phase shift and higher sloshing forces, we get higher dissipation. And the phase shift effect is actually predominant, because you can have low sloshing forces, high phase shifts, and still get high dissipation. Another thing I wanted to do is to compare my experiments with the ones performed by Lucien Constantin and his team in Bristol. Lucien was another Ph.D. student of the project, and in the beginning of the project, he did many things. But in the beginning of the project, he performed decaying experiments as I did. But his setup was radically different than mine. He didn't have a mechanical guide. He had an elastic strap. Attached to it, he had a tank, and he would put weights here that he would cut with a scissor, and the whole system would start to oscillate. When we compare both acceleration signals, remember that we have different tanks, different setups, different liquid masses. We both see an increase of the damping with respect to the dry tests. And we both see an increase of the frequency with respect to the dry tests, even when we have complete different setups. If we take the logarithm of the envelope of these acceleration signals, then we start to see some differences. In my case, we only see one slope, more or less. But he sees 3 different slopes, 3 different regimes, R1, R2, and R3, that he can actually connect to what's happening in the sloshing dynamics inside of his experiment. Why do we see these differences? Well, remember that Lucien's experiment is actually much longer than mine, since he doesn't have a mechanical guide. So he has much less structural damping, which allows for the different regimes of the sloshing to develop. In my case, my experiments are like 3-4 seconds long, so I don't get to see these different regimes. He also performed a filling level variation study, as I did, but he checked the damping ratios of each one of these regimes that he observed. And we both conclude that we see a maximum damping between 40 and 60%. For the R1 region, it's actually close to 50%. Now we're going to move to the second part of the talk, which revolves around SPH simulations. We're going to be using the following continuum model. We have a liquid domain omega that's bounded by a free surface delta omega f and some tank walls delta omega w. And we're going to be using Navier-Stokes equations for compressible flow. We have our continuity equation, momentum equation, evolution of the trajectory, and our equation of state, which is going to be a barotropic law. We're going to be looking at single-phase 2D simulations. I should underline that in the momentum equation, we have a surface tension force. And as I said, we're linking pressure as a function of density with the barotropic equation of the state. If we transform this continuum formulation and we discretize it using the delta SPH formulation, we get the formulation that you're seeing on the slide. We're going to solve this equation with the system of equations using the AquaGPU SPH code, which is an open source code developed by Zainab. We're going to be doing low resolution simulations from MY between 50 and 200. For the time marching scheme, we're going to be using a CFL equal 1 with a predictor corrector scheme and a variable time step. And then for the tank walls, we're going to be using a boundary intervals approach. Now let's look at some of the terms in this formulation. So as you might notice, in the continuity equation, there's a diffusion term, which is what gives the delta SPH name the delta part. And it's regulated with the delta coefficient that's set to 0.1. What this mass diffusion term is doing is smoothing the noise coming from the pressure field. And we're following the work from Antonio and collaborators in 2012. In the momentum equation, the viscous stresses are modeled through the work, following the work of Monaghan in 1985, where the liquid viscosity mu, it's actually the maximum between 2 things, the physical liquid viscosity and the artificial viscosity, which is regulated by the parameter alpha, which is set to 0.01 for all simulations. This artificial viscosity term, it helps stabilizing the simulations. But I should say that when we vary the liquid viscosity in our simulations, we're going to turn this parameter to 0. So we always take the liquid viscosity, and we actually get to see the physical variation of the phenomenon. Then our surface tension model follows the work from Morris in the year 2000 that takes into account the surface tension coefficient and the normals at the free surface that are computed using the eigenvalues from the normalization matrix. Then, in the evolution of trajectory to avoid tensile instability, we're including a shifting term following the work of Simon and his team of the years 2018 and 19. Now, we're going to be computing the sloshing force in aqua GPU's pH by integrating in the tank walls the pressure field and the viscous stresses. And we're going to be doing FSI simulations. So aqua GPU's pH is going to be computing this force, and we're going to input this force in our tank motion model. Our tank model is a mass spring damper system, which has a linear friction term and a dry friction term. These coefficients come from analyzing the dry test experimentally, and we'll get to that later. And so how the FSI simulation works, aqua GPU's pH is going to be inputting the sloshing force. We compute the tank motion by solving the ODE, and that's going to be inputting in aqua GPU's pH. So whatever happens in the liquid is going to be affecting the tank and vice versa. Now, let's take a look at a single phase delta speed simulation of the reference case that I showed you before. So we see that overall, the tank motion, what's happening inside, follows more or less what happens in the experiment. And then we wanted to take a different road and perform a case that's somewhat different to what we're used to, which is water or low viscosity liquids. We selected a liquid that has a very high viscosity, and such as glycerin. And we took a 39% filling level to change the filling level, but conserve the mass ratio. And we're imposing a 10 g of initial acceleration. So we see here that the dynamics are radically different. And we took these two cases for validation purposes. So you're seeing here the validation for water and glycerin cases that we published in Applied Science in 2022. So first of all, we see that in terms of acceleration and vertical sloshing force, both glycerin and water cases present a pretty good match with the experiments. We see that the water case presents a higher damping ratio than the glycerin. Glycerin tests are much longer than water cases. And when we look at the snapshots, we see that what aqua GPU's pH is given for water, it's more similar than what we see for glycerin. So in glycerin, maybe there will be some 3D effects involved that we're not really capturing. And it's important to note that here, because liquid viscosity has been increased greatly, the damping ratio has diminished. This is because the relative motion of the liquid with respect to the tank has been impeded, and therefore the water or the liquid, the glycerin in this case, is not able to dissipate more energy than compared to water. Now, I think it's important to understand the dissipative nature of this force. So is this pure dissipative, or it has some different terms? So if we can actually decompose the sloshing force that we compute from aqua GPU's pH, or the one we obtained from the experiment, in two terms. First one is going to be an inertial term, and the second one we're going to call a dissipative term. So we can see that the liquid mass times the tank acceleration plus a dissipative term, which is going to have an amplitude force and a cosine function with a phase shift, as we saw in the experiments. And then some researchers at Sapienza University, they thought that this decomposition was also could be seen as a summation of these two terms, but including two different coefficients, beta and gamma. Beta is going to be the sloshing effective mass coefficient, which basically is responsible for the increase in the frequency. Beta is a negative coefficient that diminishes the apparent liquid mass, so that results in an increase of frequency. And then gamma is going to be regulating the liquid induced dissipation, since it's multiplying the tank velocity, and therefore it's directly directed to the liquid dissipation. We can actually relate these two coefficients with F and the phase shift, for a simple decaying function. And we can test these two models in SPH, compare them for the water and glycerin cases, and we see that overall we have a pretty good match. So just to recap, the increase of frequency can be regulated with the parameter beta, and the damping increase with gamma. Now, in aqua GPUs pH, we can actually follow and track and compute the liquid center of mass, which is something we cannot do experimentally. And we know that the liquid center of mass has to be the forces divided by the mass frequency squared. And as we know, this force, it's a decomposition of an inertial term plus a dissipative term. So we can follow this decomposition. And what we have in the first term is a time position. And what we have in the second term, it has to be the relative motion, since the total center of mass minus the time position will give us the relative motion. So we want to check if the relative motion is somewhat proportional to the sloshing force, the dissipative component of the sloshing force, in terms of amplitude. So here you're seeing the amplitude of the relative motion from a direct computation, so following and tracking the liquid center of mass, and computed with the force signal, extracting the inertial part and just leaving the dissipation part. And we see an overall good match for both water and glycerin. And this means, and this is actually a pretty strong conclusion, this means that if we're only interested in matching the liquid dissipation of the problem, it's sufficient to follow the liquid relative motion with respect to the tank. Now, numerically, we can also vary some parameters that we cannot vary experimentally, such as surface tension and capillarity effects. Surface tension effects are going to be regulated with a sigma coefficient, and in its non-dimensional form, it's going to take the form of the Weber number. And then the meniscus angle, which is already non-dimensional, can be related to the bond number. If we vary these numbers, we test different surface tensions, different meniscus angles, we don't get to see much of a difference in the sloshing-induced damping ratio. This means that both surface tension and capillarity effects, when we vary them, they do not play a major role in sloshing-induced dissipation. However, if we change, for example, the meniscus angle, we get to see some differences in what's happening in the flow. If we take, for example, the first impact at 0.10 seconds, we see that for no angle, we actually don't get to see the classical radial instability that we see in the experiments. And when we increase the angle, we start seeing that two jet shape that we got to see before. But we see that overall, the liquid center of mass is following the same trajectory. So these small changes do not actually affect the liquid induced dissipation. Now we can also vary the viscosity of the liquid, which is going to take in the non-dimensional form the form of the Reynolds number. And we're going to select for reference case the Reynolds number for water, which is 10 to the 5. And when we track the tank motion, the velocity in this case, we see that for some viscosities, we don't see any change. And from some other viscosities, high viscosities, we see a decrease of the damping ratio. If we translate this trend into the damping Reynolds map, then we see that as we decrease the liquid viscosity, the damping is going to start increasing up until a threshold Reynolds number, which is of the order of 2.3 times 10 to the 4. And after that Reynolds number, the damping ratio is going to stay more or less constant. So in this region, the Reynolds number is not playing a major role. And remember that water is around here, kerosene, it's also in this order. So if we change from water to kerosene, it's not going to have Reynolds number effect. Now, to recap our dimensional analysis, we had our list of numbers. Some of them we've tested experimentally, some of them we've tested numerically, and here you see summary of all of them. So we can say that for high Reynolds number, neglecting multi-phase effects, which is something we're doing now, and conserving the tank aspect ratio, our dissipated power will depend on three numbers: filling level, inertial fruit number, or non-dimensional initial amplitude, and mass ratio. And if we conserve these three, or even if we conserve all of them, some of them won't have an effect, we see that the decay rate is being conserved between three different scales. This is a result we published in Acta Mechanica Sinica in 2020. Well, actually 2023, but we published it last year. Now, up until now, we've been talking about single-phase simulations. But as you know, there are two numbers that we left out, which are the density ratio and the viscosity ratio. So to investigate these two, we're going to implement a new formulation in aqua GPUs pH that takes into account the multi-phase effects. For that, we're following the delta pH multi-phase formulation of Hamani and collaborators of 2020. And we're going to implement it in aqua GPUs pH and see the differences between the single-phase formulation. So first, the most notable change, we see that density evolution equation turned into a volume evolution equation. For that, we had to adjust the delta 10 to be consistent with the volume change. And in the momentum equation, we have that the viscosity stresses are going to be summated within the phase. The equation of state is also going to be presenting some coefficients that belong to each one of the phases, G. And then because we're using a volume evolution equation, we have to reconstruct the density field, performing a summation within the phase of the mass particles times the shepherd, which is normalized by the phase. And then we're going to validate this multi-phase formulation using the vertical Rayleigh-Taylor instability. And this is a work we published in Physical Review E in 2021. The Rayleigh-Taylor instability, the classical one, happens when we have two liquids, one on top of the other one, and the liquid that's in the top, or the fluid that's in the top, it's denser than the one that it's below it. And this hydrostatic equilibrium is going to be perturbed, and then the instability is going to grow as an exponential function that has the growth rate in the exponent. Growth rate is going to be alpha. Alpha will depend on the output numbers of density, viscosity, on the wave number, on the surface tension, and the vertical acceleration. But in this time, it's not the inertial one, it's the gravity. Just to recap, the output numbers represent the differences in density and differences in viscosity, depending if we're talking about density output number or viscosity output number. And what we classically see in a Rayleigh-Taylor instability problem is that the denser fluid falls down and penetrates lighter fluid, forming the mushroom shape that we all know. This was actually computed with aqua diffuse pH. So our computational domain is going to be a 12 times 2h rectangular box. We're going to be measuring velocities here in this point, right below the interface. And in the first time step, we're going to perturb the interface with this vertical velocity function with a very small amplitude, a cosine function that contains the wave number that we want to excite. And then in the vertical direction, it's going to decay exponentially as we get further away from the interface. And if we take the logarithm of this measurement u, we classically or typically see three different regimes. The first one, we're going to see a lot of noise and a lot of eigenvalues competing. And then a linear regime is going to start developing. And this is the regime that we're going to be studying. And usually in this linear regime, this is what we see. We don't get to see the mushroom shape yet, because that's actually non-linear. And in this linear regime, we are going to try and fit the linear theory from Michaelian in 1996. And then after that, it becomes non-linear, and we see the mushroom shape that we all know. So if we compute the growth rate for different, which is the slope of that line, for different wave numbers and different output numbers, we see that the match between the delta speed formulation and the linear theory from Michaelian is actually pretty good. This match gets a little bit worse as we increase the output number. Why is this happening? This is because the density gradient, it's worse resolved as we increase the density difference. This is because the resolution of its simulation was set constant, therefore the density gradient is worse resolved. And finally, the last bit of my talk today is going to revolve around reduced order models. This part of my thesis was actually done thanks to a research study I did at Sapienza University in Rome, where they developed two reduced order models. The first one is a mechanical equivalent model, which is the bouncing ball model, BB in short. This is an elastic ball that's able to move in 1 degree of freedom and hits the upper and lower tank walls. The parameters of this model are these artificial parameters, which is the ball radius, the ball stiffness, ball damper, the nonlinear parameter alpha of the impacts that regulates how nonlinear it is, or the way of the nonlinearity of these impacts, and then the beta parameter, which states which portion of the ball it's actually frozen and it's not moving relatively to the tank. So that would be like which part of the liquid it's actually not sloshing. And then to fit this parameter, we're going to give it data, for example, experimental data, and we're going to minimize this objective function, J, which is the mean square error between the instantaneous damping ratio from my experimental data minus the damping ratio from the bouncing ball data. The second reduced order model are feed-forward neural networks. The one we're going to be seeing today, it contains 7 hidden layers and 35 neurons. Actually, nowadays, We're going for simpler layouts with only one layer, but back in that day, this was the solution that was proposed. We're using radial basis functions in its neurons, and this neural network in that time was trained with low fidelity coming from the bouncing ball data. Now, I have my experimental data in blue. I have the identified optimized bouncing ball, and with that bouncing ball, they generated new data to train the neural network. And here you're seeing the comparison between those three. In terms of acceleration, we see a pretty good match between the three. In terms of instantaneous damping ratio, of course, we see pretty good match since it's what the metric we're using to optimize our bouncing ball. And then we start to see some differences in the vertical sloshing force. So for example, we see that for the ball and the neural network, the vertical sloshing force, it's a bit more spikier, which is something that we don't see in the experiments. But overall, the match is pretty good. This is something we published in Nonlinear Dynamics in 2022. And finally, arriving to conclusions of future work, I can conclude by saying that I built and designed an experimental facility for vertical sloshing study, decay experiments. We have exploited this setup to test different filling levels, different scales, initial amplitudes on liquids, and all that data is made available in the database of the project, which is this link here. Actually, some of the researchers in the project have used this data to validate their CFD codes, both SPH and finite volume codes. It has been used to train ROMs, such as the bouncing ball model or neural networks. And then we also have been performing single-phase simulations to understand the dimensional relation of the problem. And we conclude that the liquid-induced dissipation depends on the fruit number, which is the non-dimensional initial amplitude, the filling level, and the mass ratio. And we also have implemented new code in AquaGPU's PH, which now it's able to deal with multi-phase flows. And we have validated this formulation with the vertical Rayleigh-Taylor stability. Now, as future work, more like current work, which is something I say it's current work because I've been working on it in the past few months. We are working on the task of giving the bouncing ball model a predictive capability. For that, we've performed 54 simulations of single-phase SPH simulations that with those 54 simulations, we're able to construct hypersurface that maps some of the physical parameters, such as filling level, Reynolds number, as surface tension effects, with the artificial ball parameters. And for each one of these simulations, we can identify one ball by minimizing the objective function. In the way, we realized that actually the ball and the liquid center of mass follow a similar trajectory. And this is something that now it's not a surprise, because we know that if we match the dissipation, so the damping ratio, the liquid-induced dissipation, then it should match the liquid center of mass. So here you're seeing the velocity of the ball and the velocity of the center of gravity of the liquid mass. And these two match pretty well because the ball is matching the dissipation of the problem. Now, we can actually take the SPH data, the optimized data, and the predicted data in yellow. And we see that the three of them for a blind test, something that wasn't tried before, has a pretty good match. And it's important to note that here, the yellow curve, it's a prediction, it's not an optimization. So the ball actually now is able to predict new cases that wasn't able before. Then in the research study, I was also able to use the laboratory of the Sapienza University and perform imposed harmonic motion experiments. I actually took my tanks in the luggage and took them to Rome and tested in their facility my tanks. And we did many experiments, but one thing that we were interested in is performing a filling level variation study, not to understand the physics, because that's something that we know now, but to generate a training data set for a multi-input neural network that takes into account different scales, different amplitudes, different frequencies, and also different filling levels. On the right, you're seeing some of the first attempts of this identified multi-input neural network, where we have different scales, different filling levels, and the multi-input neural network seems to be behaving well and matching the decaying experimental data. This is something that's ongoing work because we still have to perform more cases and more identifications of the network. And finally, we're also applying the delta SPH multiphase formulation to our vertical sloshing case. So we have our experiment, single phase simulations, and multi-phase simulations. We see that in the multi-phase simulations, we see some differences with regard to the single phase ones. We see more jets. We see that the gas phase is it's being trapped inside of the liquid phase. This is also an ongoing work, since we still have to tune a little bit this model for the vertical violent sloshing case. But one thing we can do already is change the density of the gas phase. And as we increase this gas phase, which is something that we put into before in the single phase formulation, we see that for high density gas densities, the damping of our system is decreased. So the gas is actually limiting the relative motion of our liquid by creating a damper or a cushion effect. This could be interesting if we're thinking about LNG tanks or hydrogen-based aviation. And that's all for today. So thank you a lot for your attention. And if there are any questions, I would gladly answer them.
Okay, so we should move to the Thank you very much for the presentation, Jon. Thank you. In order to proceed with the comments and questions, what we are going to do to make the session more lively and interesting is to, or at least try to, is to do kind of rounds and well, I think we will start. Who was supposed to? Yes, I'm supposed to start. You're supposed. Okay.
Okay, it's my pleasure to be the first one to congratulate the candidate for an excellent work. I think we can all agree on the great amount and quality and quantity of work you have developed. So congratulations to you and also to your advisor and also your collaborators, because it's plain to see there's lots of work here, and it's also pretty well explained. It's given us a number of articles that are very interesting, 7 at least, and some in the making. And well, I'm also the first to speak, so I don't want to overwhelm you with deep questions yet. But I do have some important doubts on reading the methodology. And one of them is regarding on you make an excellent work of finding out about this envelope by using the Lorentz transform, which is very interesting, a powerful technique, giving us very nice results we can analyze. But then you need the frequency, right, in order to get the psi or whichever letter you use for it.
Yeah.
How do you get the natural frequency accurately?
Yeah, we can get it several ways. We measure the acceleration of the tank, and we also measure the tank position. So what we actually do is select the peaks of each one of these and subtract the time between those peaks. And then you get how the period, which the inverse would be the frequency, evolves for its cycle. And then actually this was done right in the beginning, if I recall correctly. Let me go there. So here you're seeing how the frequency evolves for 3 different scales in its cycle. So for that, what I take is the mean over all the analyzed cycles, and I take the cycles up to 10% of the initial acceleration.
Okay, so a cycle. Okay, that was another one of my questions. What does cycle means?
So between 2 consecutive peaks, you define one cycle.
Okay, so then if you do that, why do you need then? I mean, if you have the time position of the peaks, why don't you just take also the amplitude and just use that to get the damping in the same way instead of using the Lorentz?
Oh, I see the question. So actually, the instantaneous damping ratio changes from cycle to cycle. What I'm doing here is make an assumption, which is actually not true. But this gives us an estimation or a suggestion of how high the damping ratio is. If you see this linear pitching is actually not true for low amplitude, because we have a dry turn that's predominant in that region. But for example, for the bouncing ball, we take the instantaneous damping ratio, we compute the damping ratio for each cycle, as you were saying. If we go to the bouncing ball results, right at the end of the talk, here, the instantaneous damping ratio actually changes from cycle to cycle, as you're seeing here. And that's a metric you have for each cycle. And it's dependent on the amplitude.
And how much is this affected by noise? Because you do have to apply
A filter, yes.
filter.
Yes. To compute the damping ratio, it's sufficient to filter at 30 Hertz using a Butterworth filter of fourth order. So all the signals that I presented here are filtered at around 30 Hertz.
Which you do numerically, or just
A post-processing, yeah, using MATLAB.
something about that. Well, then I guess my next question was about the phase shift, but I think it's the same thing.
Yeah.
Okay, and you cannot, in some places I've seen a Fourier transform, but I don't remember where, but you cannot do that for this time series, right?
It's not recommended because it's a decaying experiment. Yeah. So that the best way actually is to compute cycle per cycle and then perform the mean.
Right. Okay, I don't know where. Okay, some of my questions have been answered in your presentation, which by the way was also very nice.
Thank you.
Like I had some fundamental questions about how this was really favored instability, while the liquid was actually accelerated upwards. But then, of course, that's only in the beginning. Then it actually decelerates, and as you said, the G turns out to be upside down. So then, of course, I mean, not quite, because in the classical experiment, the acceleration is constant, and here it's varying, but you do have indeed this kind of situation. I guess it doesn't really matter, but have you ever tried releasing the tank from an elevated position instead of from below?
No, no.
Because that would very quickly, I mean, accelerate this. I mean, if you would, then you know what I mean. Then the initial acceleration would be negative.
Yeah, it's true. Yes.
And can you remind me what your release mechanism was?
A pair of solenoids.
Okay.
So we started with one solenoid, and we saw that was triggering some oscillatory movement, small movement. So we put two, so that the release was given at the same time.
So it's a permanent, non-permanent magnet.
It's a permanent magnet that's turned off
By the current.
by the current. That's it.
Oh, right. Yeah.
Okay, so maybe.
No.
Okay.
Again, congratulations for the presentation, Jon.
Thank you.
And you presented the impressive overview of your work. You made a lot of stuff. And I have two questions. Okay, the first one is about the non-dimensionalities to perform and the SPH experiments and simulations. In particular, in the non-dimensional analysis, you showed that the self-extension is the dependency of the dissipation of the damping on the self-extension and on the viscosity after a certain value is quite negligible. Okay, but these two parameters are, I think, needful ingredient to perform an SPH analysis.
Yes.
And it looks like you can, when you perform a SPH analysis, you can entry, you can whatever value of viscosity and self-extension, and so regardless the value, you get the same results. And
within some limits, yes.
Yeah, exactly. And can you make a comment on this? Because this is an interesting point that it's not easy to understand.
Yes. So superextension, it's necessary in SPH simulations. Actually, in the beginning of the project, we didn't have a superextension model. And what we saw is that the simulation became quickly unstable. So after 2-3 cycles, it was stopped. And that was because there were very, very small jets that were forming because they didn't have the surface force to retain these small jets. So including surface tension force in your simulation is actually required. Now, when you vary the surface tension when changing the liquid, that's not going to affect the dissipation, but it will change the dynamics inside of the tank somehow, but it's not affecting the dissipation. And then regarding viscosity, the viscosity variations are negligible after this threshold value. So for example, testing with water or testing with kerosene won't have a viscosity effect on the dissipation because they are so low. So it's like an effect that's been saturated.
Okay. Now, because this is a very important point, because somehow you can, for instance, in my case, train these are the models considering a tank with certain dimensions, size, and then you can generalize this model to whatever geometry without performing simulations.
Exactly, yes.
And I think that to understand this point is very important.
Yeah.
Okay, the second question is on the.
Can we maybe make rounds?
Yeah, okay.
Okay.
So it's my turn. Okay, so I would like to start mentioning that the first time I was here was 16 years ago, and I was following the work of Luis Delon performing SPH simulations on reversion tanks. So it's been amazing how here in this university they are leading this research topic, and basically they are one of the most world experts on that. I'm going to start with some comments and then a quick question before jumping to the next one. So I have to say that I found this work a somewhat outstanding work, the quality and amount, as Daniel was mentioning, basically for three reasons. So the first one is based on the research objectives are based on a H2020 project that was accepted to get the money. The second one is, I guess, you were selected among different candidates to work here. And the third one is because of the results here has been published already in index journals. So have been already peer reviewed. So I'm not the one now that's going to say that the methodology is not correct or the results, because this has been already reviewed and is already published. Then regarding the document, sorry, I have to comment that in my opinion, I found it too long. So it's a very nice piece of work for sure, but in my opinion, it's too long. And I understand it's a compendium of papers, but I'm not sure if there is need to include all of them in the, I don't know.
Okay, yeah.
Because the longer it is the more difficult it is to follow as well.
True.
And then it's also like some type of mix between being a book, because you already have some chapters of introduction where explaining everything very well, and then it's the list of the paper. So yeah. It's not a book, it's not a compendium, it's a mix.
Yeah, I just say that that's.
But you have to do what you are asked. So
yeah, UPN regulates how the compendium.
Yeah. So it's just my opinion.
Okay.
Then regarding your presentation, I think has been very clear. And to be honest, I think your level of English is so good that mine now looks worse than yours. That's my problem, not yours. I think it was again too long. Also, there were some rules here, but they found it too long. And the percentage of time you spent talking about the ongoing work was too high.
Okay.
Comparing with the, I have to say these bad things I found.
It's okay.
Then let's start with the question. So I'm here just to make SPH questions, as you know. So I will start with some easy ones, and then maybe I will try to make you some more difficult. But the first one is quite easy. Basically, you are mentioning that your experimental database is open, is available, and that other researchers you mentioned during the presentation. I have already prepared this question beforehand, but now you're mentioning in your presentation that other researchers, for their SPH codes or other finite volume methods, they are using to validate their CFD tools. So what is your comment or your opinion? Why SPH is suitable for this type of problems? Why it was selected during this project to be the CFD tool? Okay. Because now you're mentioning that also other finite volume methods can be used. So what's your comment about this?
So it's actually a huge battle in the project. There are two sides, the SPH guys and the finite volume guys, and they both defend their position as the best solution. Actually, we thought of SPH because we have large deformations of our fluid happening and we have free surface. For that kind of problems, we know that SPH is really suitable tool. Then when we look at finite volumes, in the beginning, for example, they had a problem of diffusion of the interface. So when the problem gets really turbulent with many impacts, their interface, their volume fraction was actually defunded in the domain, and you couldn't really distinguish what was water, what was air. So that was a drawback from finite volumes. But with time, they have developed their code, and now they're actually both pretty comparable. SPH also had other problems regarding including surface tension, including these delta and alpha terms that, for example, finite volume doesn't have to include. The shifting also, it's a huge thing. And so they both have their advantages and disadvantages. In my case, the choice was obvious. It was SPH because our research group developed the upper diffuse speeds code. So I wanted to learn that code and I wanted to use it for the project.
Okay, so I cannot agree more with all the rest of the panel that the work is excellent. Not only excellent, but the problem is very nice because it's a single degree of freedom problem that you study in the first year of your engineering courses. But the way you have split the problem in many subsections and more, and also how you have organized the work into different papers, maximizing the production is something amazing as well. So congratulations to you and your advisor. So yeah, I cannot agree more with them to congratulate you on this. So yeah, let me ask you a very general question. On the beginning or in the introduction of your thesis, you comment on the well, and also the project, the H2020 project is oriented to the aircraft industry, and you say that they are being conservative when designing because they always use the dry configurations, which makes sense because when you take off, you are full, and then when you land, you are empty. And in the empty situation is when you have less dissipation rates. But I think this is more interesting, not for the aircraft industry, but for truck industry, for example, where they are always filled. So what are your comments on this? Do you think that your work is going to produce changes in regulations, for example, for the aircraft industry, or they're going to be still being conservative?
Actually, my part of my role in the project was actually pretty small since I was only focusing on a single degree of freedom, but there are other PhD students. For example, Lucian, as I was mentioning, he did much more types of experiments, and he did a scaled version of the wing that I'm going to show you here. I have some backup slides just in case this was lost. So here, he's now doing post-processing this data. So he took, let's say that one of these compartments is my tank. So he's using 7 compartments and mounting them in a scaled wing. This scaled wing is a new design proposed for Airbus that's called the wing of tomorrow. This new design will include, it's going to be much more efficient wing since it takes into account this effect. And actually, if we take one of those cells, for example, in a 1 degree of freedom experiments, we get to see the structures and the mini wing of tomorrow, the scaled model. We also get to see the structure. So there are some similarities. For sure, in both single degree and wing of tomorrow, we see the increase of damping and the slight increase of frequency. We have yet to see if the same trends regarding filling level or initial amplitude are conserved in this problem, since it's much more complex. It has several frequencies, several modes, bending modes, torsion modes, and also one tank, each tank sees a different amplitude than the other one. So it's much more complex problem, but for sure it's going to have some repercussions in terms of how Airbus is going to be designing their wings from now on.
So the main problem, what is the main problem in terms of designing related to sloshing? Fatigue, for example, or what is the
thing is that the effect of fuel slosh was not included in the regulation of the design of the wings. So basically they were over stiffening their wings to account for this effect, but they realized that they can actually take benefit of this effect and make lighter wings, which are more efficient.
Okay, yeah. So can I continue?
Yeah, we'll go around. So my turn now. Congratulations again, like all the other members of the panel, to you and to your supervisor for this overwhelming insight into the vertical sloshing phenomenon. and also for the amount of dissemination you have been able to achieve. Also, to highlight that I think this is the first thesis here in this school by compilation of papers from what I know, which is an achievement too. And also I want to highlight how well all this work matches with your present teaching here in the school, in both in mostly in mechanics and in fluid mechanics, because you are in this topic, you are very well in the boundary between the two fields in a let's say very balanced way, no? And also with this optional course directly on sloshing, which we are very happy to have in this school, no? And regarding questions, for the just when you present all this data, and you know here that we have this experience on doing uncertainty assessment. And do you have any comment on that?
Yes. So the test that we have seen today, there are repetitions of 3. Each test was repeated 3 times. However, to assess the uncertainty of our nice setup, we did a campaign of uncertainty analysis where we performed 30 repetitions of the same test for water, oil, and dry tests. And here we see the dispersion graph for the damping ratio for each one of these tests. We see, for example, for dry, the dispersion is lower, and for water and oil, it's a bit higher. If we compute the running mean for this damping ratio, we see that it converges pretty quickly, and the standard deviation is also converging pretty quickly. And then to assess I'm actually following their work, which is based on ITC regulation standards, to compute the precision of the here I'm showing the acceleration signal that it could be applied to tank position or also measurements. I also saw that in the first peak, when we released the solenoids, the uncertainty was highest. So I performed a statistical study of how this initial acceleration affects the damping. So I performed tests on the initial acceleration samples and damping samples, and we see that they follow a normal distribution. So I can calculate the bivariate normal distribution, and we have a very low correlation coefficient of 0.0014, which is very, very weak correlation. We find similar weak correlations for oil and dry tests. I'm just trying to follow a similar procedure as I followed, for example, for the damp break problem that we performed.
I'm impressed that you knew that I would ask. It's incredible. Okay, let's move to the next round. Thank you, Jon. Amazing. No, so when we do this, we use non-dimensional coefficients to propagate all the.
No, I haven't done that. But that's pending. That's coming next.
I think it's.
Yeah, the dimensional numbers, I love them because I'm a physicist. It's always a good idea to express things in terms of non-dimensionality. In that regard, you have a tendency to talk about 1G, 10G. Yeah. And I think you shouldn't, because after all, it's not the G that's important. It's the fraud or this number what's relevant. Even though, of course, in our ordinary lives we have a feeling of what a G is. And also I have an issue with doing the same thing for angles, because an angle is a funny thing. An angle is already non-dimensional, so you don't need to divide it by any other angle. And on top of that, angles are funny because they don't stack up. So they're cyclic. So for example, if you have, I'm talking about these figures in which you compare, you normalize by some angles, but set by some angle. So the deviation above and below 1, which is okay to compare, but you cannot really compare. I mean, it's not the same going from 10 degrees to 20 as going from 45 to 90. You know what I mean? Because it goes around. Yeah, true. And so that obscures the very important part these shifts are having in all your discussion. So I could see the actual numbers of the angles. It will be more interesting to me because you know what I mean, no? It's not the same going from 5 to 10. Yes. As going from 90 to 180. Yes. So they're completely different things. The reason why here it was normalized, it was because the difference between them, it was low. Yeah. So it actually doesn't go around the whole. Yeah, I can guess it doesn't go around, but I want to know how close to 90 they are. Okay. You know what I mean? Sure. Yes. And that's something I missed. Okay. Yeah, and that's the only exception. I mean, I would go for comparing things all of the time.
Okay, thank you.
No, it's just, it's probably somewhere in the papers, but then again, about reading this, I agree with Alejandro. It feels like a normal thesis until you get to the actual papers, and then it gets harder. And it was my feeling just that by a little more of writing and of course copying and pasting from the articles, you could have one just a normal thesis.
Yeah.
With more or less the same amount of work.
Sure. Yes.
Which will read easier.
Yes.
Because right now what you get is, as I said, an easy reading that gets steeper and steeper, but then of course you have to go all the way up to the papers if you want to go to the.
Yeah.
It gets a bit harder.
I agree. Yes.
Okay, then I have nothing to say about wings, but I think I'm gonna pass.
Okay.
Okay, my second question is about you mentioned that the level of dissipation depends on the amplitude of acceleration.
Yes.
Okay. And I would like to understand the reason, for instance, in the illusion Constantine results, and it looks like there is a portion of the time response that has a slope that is higher than the other.
Yes.
And I would like to understand why, in your opinion, there is this kind of behavior of the sloshing distribution.
It's that's the last one. You're talking about these results.
Yeah.
Okay. So what's happening here is that he's seeing the damping in the fast regime, so in the most violent regime. Whereas I'm computing the damping ratio in the whole curve. So here I'm including all the regimes happening in my experiments, where he's only isolating the damping ratio from the first regime. If, for example, I only take the damping ratio from the initial acceleration to, let's say, 70% instead of 10%, I would get similar results as solution.
Okay. Okay, but why don't we have, for instance, a monotonical dependency of the dissipation with respect to the level of acceleration?
Okay.
So I mean, why at a certain point, a certain level of acceleration, we have the maximum?
Yes. So if we see that, we can explain by understanding the hysteresis cycles of each one of these amplitudes. So here you're seeing the hysteresis cycle for a low amplitude. So this is before the threshold. And we see that the integral of the sloshing force times the position has somewhat small area. If we increase and get further to 0.4, which is the threshold, the area gets bigger. So we're dissipating more. But when we pass this threshold, we start seeing the small loops happening in the integral. So that's actually changing the integral sign, which is adding energy to the system instead of removing energy to the system, which decreases the damping ratio.
Okay. And do you have an idea why this happens?
So it's because the system is saturating. So as I said, during putting more inertia, so physically, understanding the physical phenomenon behind it, you're putting more inertia in the liquid. So the time it's going to take for the liquid to hit the walls, it's going to be less and less. So it's the phase shift. You're basically diminishing the phase shift, which reduces the dissipation.
Okay.
Yeah, I'm going to make you now some SPH related question that you can discuss. So regarding the first source of validation, where you were dealing with single phase, comparing experiment with aquatic SPH, you have water and glycerin. So water agrees better in terms of what you were showing us, that glycerin were some discrepancies. So do you think that that can be related maybe to the viscosity treatment in the code, or maybe the equation of the state that maybe agrees better behavior for water than glycerin? What are your thoughts about that?
So for example, for glycerin, which is very, very viscous, we have assumed a Newtonian fluid type of viscosity. We haven't tried trying more complex viscosity models. That's actually something that's being done, not by me, but Javier actually does here, testing different viscosity models. So but one thing we could do to see if we obtain a better match is to test these different viscosity models for glycerin and see if that improves the mass a little bit better. Also, we have to take into account that the simulations are 2D. And when we see the experiments, the 3D structures that form in the glycerin are clearly 3D. Like So we're actually oversimplifying the problem, maybe.
Water, this 3D nature was not observed in water.
It's also 3D, but it's more, let's say, it's more chaotic. So it's like the 3D-dimensionality, it's full of noise. It's not as clear as in the glycerin case. And also we have to take into account the resolution. So actually the boundary layers forming in the glycerin case, which should be very high, are not being well resolved because we're using low resolution simulations.
And however, the solid boundaries are not so complex in this case.
Yes.
Okay. I will make a last question later.
Okay, thank you.
Yes, the guide you are using in your system is basically, as if I didn't understand wrong, is a aluminum beam with some sort of moving part.
Yeah.
So it's dry friction.
Yes, exactly.
So I mean, dry friction is something which is not nice. Something that is very non-linear, and then you have the system which is off axis with moments. And did you do some sort of characterization or study on this guide? Because at the end, most of your results are, I would say, part of your thesis is separating the dissipation coming from the sloshing, therefore what you call the delta chi from the chi sub b, which is the dry friction of damping. And then you assume that once you put the fluid inside, you have the whole system with an overall damping, and then you subtract the dry friction damping that comes from test without the fluid.
Yes.
So have you looked at if there is some sort of non-linearities? I know that you cannot, that's what I'm asking you. What are your ideas? Because another thing you could have done is using a system without dry friction.
Yes.
By using, for example, an air bearing, and then you have not this contamination or this non-linear contamination from the dry friction in your global system with the sloshing, or maybe you could have used a control damper like a linear motor, like an electromagnetic linear motor, using it as a generator. And then you can tune the force and making this like a virtual damping. I don't know, have you thought of all these? Is something that you will be doing, or?
Actually, that's I have many things to say about this. First of all, is that when we're thinking about numerical simulations, it's actually beneficial that we have a dry damping term, since it makes the simulations much shorter. So we gain computational resources. Then one of the first things I did in my thesis was perform the vertical motion with just a wooden block, so not even a tank. I would put a wooden block and I would let it oscillate to characterize the damping of the linear guide. And we arrived at the conclusion that the dry test, no liquid, it follows this differential. It could be modeled through this differential equation, which is a mass string damper equation with a dry friction term plus a linear friction. And we tested, we can simulate this ODE and check that it actually compares pretty well with the experimental dry tests. And how do we derive these B0 and B1 coefficients? These are the values. What we do is follow the methodology. That's actually in Appendix A in the first paper. What we do is assume that the damping force can be expanded as a polynomial function of 0 term, which would be the dry friction, linear term, second order, third order, etc. And then we define an equivalent damping force, which is linear, but dissipates the same amount as this infinite expansion.
Right.
And then we can correlate this linear damping force with the expansion, and we get the coefficients. And we see that for the dry, it was more or less a straight line, more or less. So that if that's fitted, it has two coefficients, the slope, which is V1, and when it cuts the y-axis, it would be the 0 coefficient B0, which is the dry damping. Then if we repeat this for wet tests, we no longer see these two compositions. It's much more complex.
Yeah.
It has a higher order terms in the damping.
Okay, so is something that you're considering using a frictionless system or a control?
Yes.
After looking at the problem?
Yes, it was thought. It was actually put as future work. The thing is also that my experimental campaign was devised to be low cost. So actually the whole thing costed around 200 euros. And I was able to draw many conclusions about the phenomenon. So maybe in the future, if we have another more like, let's say, ambitious campaign, we will go for lower structural damping to really understand what's happening and not to kill these sloshing regimes that we're seeing in other experiments.
Jumping in on this question, just we have this other system, you know, the vertical.
Yes.
For forced heat motions, in which we are using air bearings.
Mhm.
That maybe we could do something with that for this problem.
Yeah, for sure. Yeah, I would love it.
Because it's yeah, it's basically designed to do forced heat tests without these dry bearings and without this dry damping. And again, jumping into this, when you compare with the results from Constantine, his setup, from what I see, of course, you claim that his setup has less structural damping, but it seems that he is not restrained. He has more than 1 degree of freedom there, no?
That's his compromise. So he preferred to have low structural damping, but risking that you may have some relative rotation motion or some other degrees of freedom that he's not considering. That's his compromise.
Of course, you are dissipating energy in all those.
Yes, yes. I assume that in his papers, he's playing some checks that he did not to check that you're not putting energy in all those secondary directions. But yeah, that's something he's risking to do. Yes.
And just to make it a little bit faster on my side, the first paper, and because it's related to this work on Bristol, the first paper of Branislav, no, the one you referred at the beginning, this was for you a fundamental reference, no?
Yes.
And is there any other, or what did you learn from that reference that steered your research afterwards?
I'm sorry, can you repeat the question?
I mean, what did you learn from that work by Branislav that was influential for you in the rest of how you prepare things, etc.? Which results you got from them that were influential for you from this paper or any others in the past looking into this
Okay. Yeah.
experimental sloshing, let's say?
Yes. This was one of the papers. I also got the report from Airbus of this protospace campaign, and that was actually what I was following. And basically, I took into account how to treat the signals. So, for example, here they're working with acceleration signals. That I had to do dry and wet tests, which is something that may not be obvious when you know nothing about the topic. And also to record everything that you do, more or less in order of magnitude of how many times they repeated its experiments, which was very low. And also in their setup, I realized that it was not as easy to put sensors in here. So basically, they did measure the accelerations. I think they put some load cells here, but it was actually pretty hard to sensorize this. So that's why we went to a 1 degree of freedom campaign, because it allowed us to actually have redundant measurements. We have position and acceleration. And that's because our setup is much simpler. So what I learned is, yes, we have to go for a simpler version to be able to really measure everything and understand what's happening here.
Okay. Daniel?
So talking about wings, what's a protospace?
It's the name that has in the project. Airbus has a lab that's called the Protospace Lab, which is in UK. And they did this experiment there.
Because it was originally intended for future space shuttles.
I don't know if it's related to space. I don't think so.
So then what they did there was use that lever and put some a set of tanks right at the tip.
Yes.
Because that way they had more oscillation figures.
Yes.
But on a real wing, of course, you have tanks all over the wing.
No, they're comprised from one length only. So this is actually pretty representative. The tanks would go, for example, from here up to here. So they don't occupy the whole length of the tank of their wing, just as a portion of it.
But the portion that's more outside.
Actually, we can see at the new design that I showed before. I think it doesn't arrive right at the tip, but it's close to the tip. Yes.
So what's on the other part of the wings? Because I don't know nothing about.
As structural components, you have the the skin of the wing. You have many, like most of all structural components, and also a lot of empty space because it has to be light. It has to be a light design.
Ah, okay, so just make it empty. And you, okay, so these times, in order for these results of yours to be representative, they're filled with kerosene,
Yes.
and of course, in a real flat situation, they are filled and then gradually empty
Yes.
as the plane flies. And I guess each one of these tanks is independent from the others, and
They have checked different configurations with baffles that are not where the what happens in one cell doesn't affect the other one. And then, for example, Lucian's test in the wing of tomorrow, which I'm trying to get to, he actually has entries between tanks, so the liquid can actually go from one side of the tanks to the other one. And that's interesting because the filling level varies from one tank to the other one, depending on how the amplitude goes.
yes. So that's of course what's suggested by your results, right? It's better off for the overall plane stability to have all of those tanks at the same level, and that level be about half filling level, right?
Yes, so here you can see that here the filling level is lower and it gets gradually higher as you reach the root of the wing.
But that's one of the configurations.
Yes.
So where's the plane? Where's the body of the plane in the picture?
No, it's a counter leverage wing.
But where would it be in a real setup, in a real plane?
In the wing, it's the wing.
Yes, and where's the plane? The rest of the
Oh, here. It will be the fuselage and here the wing.
And I can see your relation.
So this is where the root of the wing ends. It will be
Yes.
the fuselage.
Okay,
So it's like this. And then you have the other wing here.
okay. Right. So do you have any further suggestions on the actual applications of your results in general to set up or filling level of actual wings in aviation security?
Well, from the scaling that we did, when we scale up the forces up to the wing size, we see forces of 2,000 newtons from only one cell. Okay. So if you multiply that, roughly speaking, for 7, then that's the force that you would be getting, more or less.
That's what you want, like for turbulence, for example.
Yes, turbulence, landing impacts. When you're landing, the wing is also going to do like this. It's going to extend the sloshing process.
Yeah, that's interesting. Thank you.
Okay, okay. My last question actually was about spatial characterization, but you replied to this question, but I have another one. In particular, concerning the non-dimensional analysis, it looks like the main numerical parameter is the vertical height of the tank. So I wonder what will happen if your experiments you insert a buffer in the middle of the tank, such that the overall mass is the same, but the aspect ratio of the two different tanks divided by the buffer is different with respect to the original one.
So you say that the length, you're halving the length, you're making it 0.5.
Yes, the lateral length.
Lateral length. But the liquid mass is the same,
Yes,
then you wouldn't see much of the filling level is the same.
yes,
You wouldn't see if the liquid mass is the same, you wouldn't see much of a difference.
okay,
That actually is what we do when we put the fruit scaling gains in the, for example, the neural network. We take into account this mass effect when we multiply the mass of the model divided by the mass of the other experiment. And if the mass is the same, then there shouldn't be an effect.
okay. So because the aspect ratio are really different between the lengths. Okay.
Well, just jumping on this, but of course you are somehow restraining the wave numbers of how this develops vertically, no? Let's say that you, instead of making 2, you make 10 divisions of your tank. How this develops in terms of all the splashing and the dissipation.
Yes, but remember that the mass is the same. So somehow you're increasing the density of the liquid to match the same mass. You're reducing the space, but you're keeping the same mass constant.
Of course, but how the fluid dynamics develops is.
It's going to be different locally, but I don't think that will affect the dissipation overall.
So only
if the mass is,
only the initial transient is influenced by this parameter.
sorry?
I said just only the initial transient is influenced by the.
Yes, exactly, yes. So if you look at the flow, it's going to be different depending on the locally, it's going to be different depending on the length. But I don't think that's affecting the total dissipation. When you see it globally, after the first impact,
I think it would, I mean, if you have 10 divisions or 100 divisions, this would behave completely different from the fluid dynamics point of view. I mean, this is also a dimensional problem, but well, you are thinking about that, no? Or
Probably in a certain range. There is not this.
yeah, in maybe half, not a difference, but if you make many divisions,
you mean in the limits? Like,
yeah, in the limit.
okay, yeah. If you exaggerate that number, then yes, because then you would also have like very strong sursuspension effects, since you're making that very, very small.
Well, you are not allowing transversal modes to develop on the flow, so you would the amount of energy that is transferred from one thing to another would be reduced. I think. Well, sorry. Yeah. Continue. Sorry.
Okay, so now I will have a very last question and a last comment. I have other questions related with SPH, reason, things like that, but maybe we can discuss about that later. So my last question is, since you have been involved in this project with an important industrial partner, and you have been learning about how to use an SPH code, what do you think that us from the SPH community, what we should do to encourage the use of SPH in industrial applications? What do you think that, because in our SPH community, one of our main concerns is how to convince industry to find attractive and robust enough SPH to be used in consultancy or projects like this. And this project is because it's a mix of research and application, so that's why SPH is involved. But what do you think, in your opinion, after this experience, what we should do to encourage the use of SPH in industry?
Well, from my experience, which is limited to this project only, I don't know if this is the same in other projects, but the people who were working with SPH were able to retrieve results faster than the people working with finite volumes for this concrete problem. So if you're looking at very violent sloshing flows with large deformations, I would go first for an SPH solution rather than finite volumes. And so that's what I would say to the industry, that if you want to have results a bit faster in finite volumes, I would go for an SPH formulation.
Okay, well, yeah, SPH have also some other advantages that maybe talking about computational runtimes cannot be fair enough, because comparing codes sometimes depending on the execution device and a lot of things are difficult. But this is something from the SPH community we are always worried. And basically, what we're trying to do is to face problems where SPH can give you a more accurate solution than others.
Yes.
Well, so my last comment is I always say congratulations at the end. I prefer at the end. So I would like to congratulate you for your work, because I think it's a very nice piece of work, and your supervisor, and then the rest of your colleagues working with you. And I hope that based on the number of journal papers you have and your curriculums and experience, and the number of journal papers, I would like to highlight that they have been published in a short time of period, but in what I consider proper journals and editorials, rather than going to this type of new predators. And I think that that's something that should be highlighted again. So I hope that you take advantage and you keep working on this, and with other industrial partners saying very good words about the SPH.
Okay, thank you very much.
I have many questions,
Yeah, go on.
but I'm not going to be the boring type. Let me make some of them only. So one is, again, from the practical point of view, if you look at your experiment where you have these bars with the filling, height and thing, you have 0.5 no as a magic number where you get this maximized dissipation. In a practical application, this filling is varying during flight, let's say. And also it's very counterintuitive, no? you want to have a large volume of fluid inside to get large dissipation and then reduce vibration. And that obviously only happens in a certain time. Like, is there something that you can do to make this flat? Like you could add some geometries inside. Have you thought? I know that the industry is not doing it and you haven't done it. So probably it's just a question on, is there something that you can think of to control the, before I was talking about the dry friction control. Now my question is more about the ways of controlling the fluid sloshing, the fluid damping. For example, could you make geometries inside the tank that promote a better distribution, dynamic distribution of the mass to make, for example, these in between 0.4 and 0 and in between 0.6 and 1 to grow higher, because this is what you want.
Yes.
So you haven't thought of it. No? I'm just giving you a lot of work.
Yes. We did a small trial in the beginning, in the first year, where we included a sponge inside of the tank.
Okay.
That was actually a suggestion from the coordinator that comes from Airbus. And all the configurations we tested, including the sponge, was not enhancing the damping, was actually making the damping lower. And all the other configurations that have been tried, including baffles in the project, they did not enhance the damping. They actually, you're actually making, not allowing the liquid to move as it should. So therefore that's diminishing the dissipation. But I've been thinking about this, and academically,
I was more thinking into geometries, not because a sponge is very complex media, no? But
no, in geometries, I haven't done any trials. Testing different geometries. What I can say is, for example, when I went to,
you've done enough.
Yeah. Well, we tested a different tank when I went to Rome. I brought my tanks, but they had another tank there. Actually, Saltari here can explain as well. So that this tank was different geometry in terms of height, length, and width, and we arrived to similar conclusions as well. But
but let's say you add protuberances in the, that conduct the flow in some strange way, I don't know.
But maybe that's helping sometimes, but then other times it's going to be a wall that's going to basically impede the movement. So
but it could be not impeded laterally because you haven't done any analysis.
No, I haven't. Actually, I haven't really.
So it's something that you should probably think. Yeah.
Okay, I will.
It might be interesting because you already have all this setup, and should be relatively easy to build the geometries on the floor of your tank.
Yes.
And play with it.
Yes.
Can I continue?
Yeah.
The other thing I was, and I will finish because so this type of problem could be also understood as a tuned mass damper, let's say.
Yes.
So, and the physics of a tuned mass damper, or the idea behind the tuned mass damper is that you move from a single degree of freedom to a 2 degree of freedom problem, in which one of the degrees of freedom is the oscillator, the fluid oscillator. It could be a pendulum, a moving mass, and in your case it would be the fluid. Have you done some analysis on the motion of the I know that you have calculated the center of mass of the fluid, and you have done, but have you tracked the frequency change of this bulk of fluid moving and put it into perspective to the original frequency? That means, so your system has a natural frequency. Now you add the fluid, you're changing it, and you are basically producing a 2 degree of freedom system. One is the structural power and the other is fluid mass. Yes. So you would kill all vibrations in for example, in a force harmonic motion test, when the natural frequency of the fluid itself would match the natural frequency of the structural part alone. Have you done some analysis on this?
We went to Rome. So the thing is, if I calculate this sloshing effective mass parameter, which basically regulates how much the frequency increases or increases with respect to the tri-tests, so I do it in my decay tests. It works, but it's not a very robust measurement. Actually, when I went to Rome, in there they have imposed motion, so there it's actually much easier to characterize this sloshing effect with mass effect. And you can actually characterize this effect for a wide range of amplitudes and frequencies. And interestingly enough, when you go to high frequencies, there is some resonant phenomenon happening for very low amplitudes and high frequencies, where this parameter actually becomes very, very important. But in my experiments, I just limited myself to calculate it, but I haven't really done any more variations.
I could also think of the problem as a 2-degree of freedom. Then maybe you can find the whole things. Another question I have is related to one question that Daniel did before, and it's related to the fluid, to the sloshing force itself, because it's not harmonic. Very complicated. You're filtering it, and you're only getting you're cutting off a frequency. And then you are computing all these phase force phase plot based on this after the filtering and everything. Have you done some analysis on computing the real or the real time or the time varying phase of the signal by using, for example, Hilbert transforms or analytical signal or something like this?
Yes, with the Hilbert transform, I'm also able to retrieve the phase shift. That's something I can do. And I get to similar conclusions when I computed with a Hilbert transform and just with the time shifts.
So it doesn't change.
It doesn't change much, no.
So, but that's always after filtering, no?
Yes, yes. Yes, I have to filter it around the natural frequency, so I get only one peak per cycle. If I have other frequencies, I'm not able to identify the maximum peak.
Now, the question was because if you use the analytical signal, for example, to compute the instantaneous phase shift between the two signals, one is almost harmonic, and the other has many components that come from all this splashing and all these very complex fluid flow phenomena at the time. The question was, is there some changes? But for what you're saying, you're always doing this analysis with applying a filter before. So
yes.
Therefore, you're killing all these.
Yes.
All these parts in another question I have.
Can I jump in?
Okay.
One jumping on the previous one by Frank. There is a fundamental difference between this problem and the anti-roll tank problem, no? In the sense that in this problem, you have a structural system which has a natural period or many, but one first natural period. And then in our case, in ships, in roll motion, for instance, you have this natural roll motion. And then you would have, let's say, the natural sloshing period, no? And the interesting part is when you couple both. But here you have the structure has a natural period, but the fluid, or at least it's not clear which natural period you have because you don't have a harmonic oscillator in terms of the vertical motion, unless you look into maybe standing waves,
Yes.
which of course the frequency is much lower than any structural, no?
Actually, in one of the papers, we did that. We took the final cut of the simulation when it's a standing wave. And there we could fit this sloshing frequency and the decay rate of the standing wave to the final end of the experiments. But that's not something you can do in the violent routine where there are many things happening and the sloshing frequency is lost.
But you can do this on SPH numerically, no?
Yes, yes.
Well, but the question is, following this one is whether you plan to connect all what you learned here in terms of maybe looking into anti-roll problem, anti-roll motion,
yes,
dampers and these kind of things that we have some experience.
Yes, of course. Yes, actually, for that purpose, the sloshing subject that I'm teaching here is also very helpful because they do an anti-roll time with USPH, and some of the conclusions they drive from their variations in their work, it's pretty similar to what I write here. So actually, there are some differences, but they're not so different systems.
Any question, Daniel?
Regarding this identification of your problem with some other well-known problems in this school, like if big problems, etc. and all this sort of problem. I was a bit confused when you introduced your beta, and I was thinking this would be the added mass, but then it's negative,
It's negative, yes.
so it's not an added mass, it's
It's decreasing the mass. In that way, the frequency increases. So if you think of as Fran, what I was saying before, this 2 degree of freedom system, no liquid, and you excite this vertically, the second mass, it's gonna move in, it's gonna be shifted some way with the main motion. And that's gonna decrease the apparent mass that's moving in that direction. So that's gonna increase the whole frequency of the system. The same effect we're seeing here, that's replacing the secondary mass with the liquid.
so it's completely different or complementary to what happens in C,
Yes,
usual C structures.
yes.
And so with negative, you can always split it in small, large, but always negative. Thank you. Well, that's from my point. Have any?
Okay, I'm afraid just a comment concerning your question, maybe about the disorder models. I was wondering which are if there is an application in marine engineering that fits the use of neural networks.
Yes.
And maybe the use of identification of sloshing anti-roll could be one of these things.
Yes, actually, in the anti-roll facility we have downstairs, I think it would be a good idea to perform some experiments, thinking that data will be used as training for a neural network. I do think, however, that the neural network that we would have to define for anti-roll is significantly different than the one we're using here. So that's something we will have to think through. But yes, it could be done, and I think it's pretty useful. And I'm not sure if someone has done it already.
Jumping on this of the reduced order models that there haven't been many questions in this. Do you think, I mean, did you obtain, because of course from the experiments you obtain insight into the physics. From the numerics, you have changed the parameters that you cannot do in the experiments, and you obtain insight into what is going on there. But from this ROM, do you learn anything actually?
So it's not the best tool for getting physical insights on the phenomenon. But once you have an reduced order model that's able to predict something, you can use that model to make predictions about the physics. And maybe it helps you understand or run faster cases than in aqua diffuse pH. For example, if I want to do a frequency study, different frequencies, that in aqua diffuse pH is going to take very long. But if I have trained a neural network, I can do the same and then derive some physical conclusions of the results. But the tool itself, it's not helping me understand. But I can use the tool to derive conclusions if I have trained it properly.
Okay. Any question, Alex, or no?
No, we covered it.
Okay.
I don't want to be boring. Congratulations again.
Thank you.
For the amount of work.